Om Swastiastu. Assalamualaikum warahmatullahi wabarakatuh. Shalom Nama Budaya. Uh, in this video, I will explain about chapter 4, the metallurgy for the non-metallurgist. But let me introduce myself. My name is Putra Hutabarat with student ID number 230553107. I am from the Mechanical Engineering Study Program, Engineering Faculty, and Udayana University. Next. Chapter 4. Discovering Metals, a Historical Overview. The ancient world passed from the Stone Age through the Bronze and Iron Age to our modern developed society, a society that is dependent on metals and alloys for its very existence. However, an impressive body of metallurgical knowledge developed in the thousands of years since ancient man first found copper and became curious enough to investigate the behavior of this naturally occurring, relatively pure native metallurgical knowledge evolved from an art to a science until the body of scientific knowledge on how each metal and alloys behaves has become quite extensive. Next. 4.1 Native metals. Most natural metals are in the form of minerals or compounds that have reacts with other metals or non-metals atoms. Metallurgists extract metals from compounds except that some metals occur as pure metals. Metallurgy developed through the use of these pure metals. The calculated period before the Bronze Age, estimates 5000 to 3000 BC, marked the mystery of metals. Initially, gold, silver, and copper were used for decorative purposes due to their low strength. However, the Copper Age paved the way for practical metallurgical. Copper, like gold and silver, was found naturally and used for ornaments and decorative purposes. Ancient civilization in Egypt and the Middle East discovered that hammering copper made it stronger. They used this nanotechnology to create usable tools and knives for agriculture and fishing. However, copper knives lacked strength for combat around 4000 to 3000 BC. They learned to extract copper from bluestones and minerals, expanding their sources. The development of high temperatures to melt copper also expands the amount of material available. Large pieces of copper could not be cut and therefore were not of significant importance until melting techniques became available. 4.2 The Bronze Age. The Bronze Age started with the discovery that combining metals created stronger alloys. This strengthened copper in the Middle East. Bronze alloy containing 87% copper, 10 to 11% tin, and trace amounts of other elements. Within 4000 to 5000 years, the Bronze Age emerged. The sterling silver was developed by adding copper to silver. The addition of 7.5% copper increases the strength of silver without changing its appearance. Practice of ancient metallurgy persists into modern times, with bronze consisting of 88% copper and 12% tin. Similar to ancient bronze, increased tin content leads to hardened gun metal with 88% copper. Evolution of metallurgical practice from copper to bronze is hard to trace. Early attempts produced arsenic containing copper alloys. Arsenical bronze, stronger than usual copper, result from accidental inclusion of alloy element in ore. Ancient metallurgists intentionally mixed copper and tin ores to create bronze, marking the real onset of the Bronze Age with properties similar to modern alloys. Next, bronze stronger than pure copper was used as both a tool and the weapon. Picture 44.1 shows a photograph of an ancient bronze casting. So casting Chinese foundry technology in the 8th century BC, it has less tin than typical bronze weapons. Although tin bronze was made due to scarcity of tin, copper-rich ores were more abundant, so unalloyed copper was used when possible. Bronze was expensive and transportation of tin was difficult. The shortage of tin made a crucial material during the Bronze Age. Next, 4.3 Making metals. Extractive practice is table 4.2 Common occurrence of metals. Most metallic elements occur naturally as minerals or ores, which are compounds that result from a reaction between metallic and non-metallic atoms. Common native and mineral occurrences of metals are listed in table 4.2. Most copper, zinc, and lead ores are sulfides, while iron and aluminum are generally found in oxide ores. Minerals are often colorful and attractive, leading ancient and modern humans to collect samples. A common copper sulfide mineral born turns iridescent blue or blue-green when exposed to air due to a chemical reaction with oxygen. Other copper ores include chalcopyrite or yellow and copperite deep blue. Metals are extracted from ores by separating them from sulfur or oxygen, which requires energy. This can be done by heating mineral samples, accidentally causing copper metal production, or intentionally casting stones into a fire during worship and discovering transformed copper. Next, pyrometallurgy extracts metals from ores using chemical reaction at high temperatures involving processes like roasting and smelting. Other methods include hydrometallurgy and electrometallurgy. Hydrometallurgy uses acidic or alkaline solutions, while electrometallurgy uses electrical energy for extraction. Copper smelting began in the Chalcolithic period after the discovery of melting copper. As native copper and sulfide ores deplete, metallurgists extract copper from other deposits. This led to the discovery of alloying and the Bronze Age. Extraction processes are complex, but smelting can be simple. Early settlers used galena ore to produce lead for bullets by roasting it in a tree-stump fire. Although extraction of lead from galena has been common for many years, it has only recently been recognized that silver is associated with the extraction of lead from galena. Lead sulfide ores generally contain significant amounts of silver. Because of the potential for simple recovery, lead smelting is currently carried out under controlled conditions. This picture is about picture 4.2 again. Systematic of lead blast furnace shown in Picture 4.2. Pyrometallurgical extraction process in furnace heating or in controlled environment to produce desired metal and undesirable products. Poisonous hydrogen sulfide gas is produced during lead smelting due to the reaction with oxygen in the air. Next, 4.4 Iron. The early name for iron means stone from heaven in several languages. This name probably resulted because the first iron used by ancient man was literally from heaven. Meteorites weighing from a few ones to tens of tons have been falling on the earth since its beginning. First iron likely obtained from naturally occurring iron oxide deposits when primitive man put fire at iron-rich cliffs, resulting in iron sponge for tool fabrication. The first iron developed was forged iron, which could be shaped easily using a hammer. Wrought iron contains a small amount of carbon, less than 0.05%, which makes it flexible. Iron with a content of 0.1 to 2.0 Wt%. C is called steel. Next, iron smelting. The discovery of an accidental drop of copper sulfide or probably also occurred during the first drop of iron oxide, or the observations of ancient metallurgists led to the production of iron by utilizing carbon-reducing oxide ores. The use of this technique spread in Egypt in 1500 BC and remained in use for 3000 years. Iron oxide ores are found worldwide, and ancient civilizations in Egypt, China, India, Africa, and Malaya all independently developed similar iron-making practice. The resulting metal, known as wrought iron, was pure, soft, and malleable. Next, this picture of 4.3. However, the carbon also serves as a reducing or reducing agent to free the iron from the iron oxide. The carbon reacts with the iron ore, forming carbon dioxide and iron. Early iron smelting operations were conducted in semi-furnaces, such as the one illustrated in Picture 4.3. These furnaces could easily have been developed after the first accidental reduction of iron oxide. Improved furnace designs allow higher temperatures to exceed the melting point of iron. Molten iron dissolves carbon and impurities, producing pig iron. The raw materials and production processes are different from raw iron. Blast furnaces are caused by air explosions. Next, this picture is picture 4.4. The use of blast furnaces greatly increased the rate at which iron could be produced. A systematic of blast furnace is shown at this picture. In such a furnace, approximately 2 units of iron ore, 1 unit of coke, 1/2 unit of limestone, and 4 units of iron ore to blast are required for each unit of pig iron produced. The smelting process in a blast furnace begins when the charge of ore, coke, and limestone is loaded into the top. Temperatures in the blast furnace range from the 150 to 200 degrees Celsius. Due to the hot carbon monoxide from the coke combustions, carbon monoxide reacts with iron ore, forming iron, carbon dioxide, and salt. Salt removal is a challenging problem in metal production. Next, this picture is picture 4.5. The controller of production practice to produce high quality products without the contamination of the iron environment is a relatively modern innovation. Environmental contamination was not considered a problem until recently. However, the production of soot was well known, as illustrated in picture 4.5, which is a drawing of an early version of the blast furnace. This drawing appeared in Georgia's Agricola book De Metallica, which was prepared in 1556 and translated from Latin into English by Herbert Hoover and his wife Lou Henry Hoover. Steels are iron alloys with 0.1 to 2% Celsius, combining the toughness of raw iron with the strength of pig iron. They are made by heating raw iron in a corporeal fire, absorbing carbon to form a solid solution alloy known as steel. Next, 4.5. Discovery of modern metals. Beryllium is added to copper to improve its strength. The copper beryllium alloys contain only a small amount of beryllium, approximately 2%, but can proceed or heat treatment to be much stronger than any low tin brass or copper zinc alloy. These very high strength copper alloys are used for the production of springs in the electrical industry and to make non-sparking tools for use in potentially explosive atmospheres. Next, cadmium. Cadmium coats zinc, protects nuts, bolts and other components made of high-strength steel from corrosion. Commercial aircraft components are often cadmium plates. Cadmium strengthens dental fillings, but efforts to find a safer alternative are underway due to environmental concerns. Chromium was discovered in 1798 and used mainly as an alloy addition in steel production. Chromium is crucial for the steel's resistance to oxidation, corrosion, and strength improvement. Next, molybdenum was discovered in 1781 and is primarily used as an alloy addition to steel. However, molybdenum melts at 2620 degrees Celsius or 4750 degrees Fahrenheit compared to 1535 degrees Celsius or 2795 degrees Fahrenheit for iron. And next, tungsten was first refined from ore in 1783 and was originally called wolframium. Tungsten was first used as the filament for the incandescent light bulb and this use accounts for 15 to 20% of all tungsten use. Next, vanadium. Vanadiums are among the hardest of all relatively pure metals. It was discovered in 1830 and is actually more abundant than copper, nickel, or zinc, but it's very difficult to verify. Magnesium is the lightest of the widely used structural metals because of its low density. Magnesium has been used in aircraft frames. It is also an important alloying element in aluminum. Next, titanium was discovered about 1790, but because of the difficulty of freeing titanium from oxygen and nitrogen, it was not readily available as a structural material until the 1940. Next, iridium, rhodium, palladium, and platinum are, along with gold, termed to precious metals. They are all very dense and very corrosion resistant. However, the term precious metal comes from the fact that all these metals are expensive. Next, aluminium, the third most abundant element on the face of the earth, is a member of the family of metals that includes gallium, indium, and thallium. Next, 4.6 Refining of metals. Purifying extract metal is known as refining of metals, which involves ancient practice and modern advance. Gold can be separated from minerals through penning and sluicing due to its higher density. The remains of gold flakes or pieces are not always pure. Additional purification steps may be required. Gold refining is a relatively simple process that involves heating gold to very high temperatures. The reaction of the oxides from a light layer that floats on the top to liquid gold like flakes floating on water. This technique has been known since 2000 BC and 1000 BC. Metal refinement techniques are more complicated but involve similar phenomena, can produce very pure metal. Next, modern refining practice produce high quality metals and alloys, but they can be costly and impurities are common. Although very high purity metals are typically too soft for structural applications, the small amount of impurities in some commercial pure metals imparts adequate strength for some structural applications. Next, this picture is picture 4.8. For example, commercial heat exchangers for certain applications are made of commercially pure titanium. Although titanium is characterized by a somewhat low thermal conductivity compared to that of other metals such as copper-based alloys, the major design factor in heat transfer relates to material thickness, corrosion resistance, and surface films, not just to the thermal conductivity of the metal. For these reasons, commercially pure titanium can have advantage over other metals in the design of heat exchangers. It offers good strength, resistance to erosion and corrosion, a very thin conductive oxide surface film, and a hard smooth surface that limits adhesion of foreign materials and promotes drop-wise condensation. Okay. um, I think that's all I can explain. If there are any wrong words in the reading, please forgive me. That's all, and thank you.